I had a 93 and I didn't do, okay, I got 4 points on one assignment, 4 points total.
Okay,
It was 91, I was
close them up. Let's have a look here.
Click them closed or at broken.
Exactly.
You're not quite a student.
Let's get rid of anything, any distractions, that'd be great, thank you. Here's where we left off. Boy, it's been a while ago. It would have been last week, right? So we looked at our second technique. We know how to factor two-term polynomials with our our patterns, factoring patterns. A cubed minus b cubed, a cubed plus b cubed, a squared minus b squared, and there is none for a squared plus b squared. There is no sum of squares pattern. The next step was how do we factor three-term polynomials? And the only way we really know how to do that is by using a quadratic pattern. So the one we looked at, if we had something like this, where we had x to the fourth plus 15x squared minus 16, if we group this up into packets of x squared, it looks quadratic, doesn't it? Then it just looks like hand squared plus 15 hand minus 16. We're going to have to factor that. That's just hand plus 16 times hand minus 1, right? Okay? Well, hand is x squared this time, though. It's not x. Okay? But the pattern stays the same. So we factor it using magic numbers just like we did before. But what we end up getting out of that is not just the answers negative 16 and 1. We get x squared equals negative 16. Or x squared equals 1, right? And then we got to solve those. We got to go one step further with those. So if we're just factoring this completely, that's what it asked us to do. That's as far as we can go. We can't factor this because it's a sum of squares, right? It's x squared plus something squared. This is a difference of squares, though. X squared minus 1 squared, and so we can't. Now, what if we had the very same problem? What if we had the same problem, but we're trying to solve the equation, right?
Why
So,
can't you break down the 16 into 4 and 4 like you just did the other one?
well, you can. It's x squared plus 4 squared, but there's no pattern for a sum of squares,
Oh, okay.
right? Okay, but what if we were trying to just set this whole thing equal to 0? So we got it factored.
Crazy.
It does look crazy, but look what it's gonna work out great. How about that? Okay, so what if we were just solving an equation though, right? We wouldn't have had to factor it any further. We used our trinomial factoring pattern to break it apart into two manageable pieces that are quadratic. Now all we'd have to do is just set these equal to 0. Right, and just solve it, right? Subtract 16, square root both sides, so x would equal plus or minus 4. What? I, good. Because I'm square rooting a negative. And then over here on this one, we would just get x squared equals 1, so x equals plus or minus 1. So I get 4 complex zeros, right? Okay? If we look at the graph of this thing, of this function, there it is. Okay? So notice that we got 2 real zeros, so those corresponded to x-intercepts, and then I got 2 imaginary zeros, and those do not. We get a very strange shape to this function, don't we? Because it's got our two, we've got our two, it's supposed to be a different function.
Looks like
That looks different.
It is a little different.
Yeah, because the equation we had was
I think we
x to the
accidentally
4
opened
minus.
Yeah, I think I did a different problem. But this is kind of the same thing though. We get a situation where we get 2 real solutions which correspond to our x-intercepts. And then we get 2 imaginary solutions which make the function do weird things, make it turn and do some weird stuff. It's not just a regular parabola, but we did only have 2 real zeros. Right? The 2 imaginary zeros are responsible for what the shape of the function. Okay. All right. So for today, Today we're moving on to, so we know how to deal with two-term polynomials using factoring patterns. We know how to factor three-term polynomials using our magic numbers, right? Now we're gonna move on to four-term polynomials. Okay, and I wanna lead into that by just showing you a couple examples of this new technique. It's called factoring by grouping. And it works for other situations too. Like in this case, what would the numbers have to multiply to? 40. Negative 40. So what numbers multiply to negative 40 and add to what else? So what would they be? There you go, negative 10 and positive 4. So factoring by grouping, now if we just take that middle term, this actually, in this case, you're going to think, well, why would we do this? It makes it harder, but it's going to make it easier on some of the next examples. So we're going to take that negative 6x and we're going to break it up into negative 10x and positive 4x. It doesn't matter, either order, it makes no difference. It makes no difference. So we'll split this thing up, split that middle term, and we get a four-term polynomial. And we recognize that these two add to negative 6x, right? Okay, here's how grouping works. Grouping applies when we have four terms. And you can do it with even larger numbers of even terms, or even numbers of terms. We're only going to do it with four. So if we have four terms, we're just going to split this thing down the middle, and we're going to make two groups, one group of two and one group of two. The process is just this. We're going to start off with that first group, and we're going to ask ourselves, what is the greatest common factor of the first group?
X.
X in this case. Good. So X is our GCF, right? Okay, what's left over when we factor out an X? So if we divide each of those by X, what do we get?
X
Good, X minus 10.
Oh, we know that.
So then we get this other group, and here's the rule. Now this is the part you got to pay close attention to. The other group, we're going to do the same thing, but the restriction we have is that we need the leftover factor that we get to be the same in both groups. So in group 2, if this is going to work, we have to have an x minus 10 there also. And then we just have to ask ourselves, can we do that? Can I factor something out and be left with an x minus 10? Well, what times x is 4x? 4. So we're gonna addition 4 and see if it works, right? Well, if I distribute it, I get a 4x, that checks, and I get a negative 40, that checks. So it does work, right? So this thing does separate like we need it to, and we're gonna factor by grouping. And the only other thing we have to do here now is, why do we do this? Well, look, we got common factors in each group. So I can factor out the common factor, which is the x minus 10, right? That's the one that we knew had to be the same factor in both groups. So if we undistribute that, look what we get.
Does that matter that it's one of the magic numbers, or is that just a
Coincidence.
coincidence?
Coincidence. So x minus 10, and then what's left behind? Well, we end up with an x, because when I undistribute the x minus 10, those are divided away, aren't they? Right? So I end up with x plus 4. And what do you know? Those are the factors. Those are our magic numbers, aren't they? Right? Yeah.
So I can go from that.
Yeah. Okay, so you're thinking big deal, but here's where it's really helpful. Now look at this problem. This is one where we would have to use bottoms up because a is not equal to 1. Okay, so we got to remind ourselves when we're finding the magic numbers to do bottoms up, how do we get them if we have ax squared plus bx plus c in our trinomial where a is not equal to 1? They have to multiply to what? And add to what?
Oh, wait, no. No, it's not.
Is it?
Bottoms up was literally like 2 years ago.
It's been a long time since we did this, I agree. a lot of math stuff. They multiply to A times C, to AC. Well, what is AC? 60. We'll just, all we care about are the coefficients, so 60, okay. And they add to B, which is,
Oh.
okay, so then that means that our magic numbers are what? Negative what, negative what?
Negative 3.
Negative 1
You got point that.
and negative 3, good, okay. So then we're just gonna split up the negative 23x into those two separate terms, right? So this will look like 15x squared minus 20x minus 3x plus 4, right? And we're gonna just split this thing down the middle, right? Same as before. What's my greatest common factor this time in the first group? 5x, okay.
So you're basically just taking a trinomial and making it into two binomials
Right,
by,
We are. Yep. By choosing the magic numbers to split them in. Yeah, exactly. So then what are we left with here? Okay, 3x minus 4. There you go. Okay, plus, I always need a plus sign to separate the two groups, right? In the other group, I know that I need to have a leftover factor of 3x minus 4. Well, what times 3x is negative 3x? Negative. Okay, so then negative 1 is the number we have to see if it works. Negative 1 times 3x gives us negative 3x. Negative 1 times negative 4 gives us plus 4, so it works. So what can we factor out of each group?
3? Nothing.
There is.
1.
Look at the, so now let's look at this and at the structure of this whole expression here, right? So we've got group number 1 has how many factors?
1.
Now, hold on here, you're just throwing out numbers.
2.
Factors are things that are being multiplied together. Terms are things that are added or subtracted, right? So how many factors? We get two terms. We get this first term plus the second term. There's two things being added here only, right? In the first term, how many factors are there? 2. I get the red one and the blue one, right? Second term, I get 2 factors, the red one and the blue one. What's the common factor in the two groups? 3x minus 4, right? So we can factor out 3x minus 4, and what's left behind if I do that? So those are going to cancel. Right, I'm going to get 5x plus negative 1, so 5x minus 1, right? You guys see that? Okay, so that's one way you can factor, if you can find magic numbers, you can always use factoring by grouping to factor a trinomial, if magic numbers exist.
When you do that last part again, where you got the 3x minus 4 and 5x minus 4.
Okay, right, because now look, I've got 2 factors in the first group plus 2 factors in the second, so I'm going to undistribute the 3x plus 4. Then what does that leave behind? Now it's gone. So I get a 5x plus negative 1. Okay? All right, so it's helpful, it's kind of a good way to do harder trinomials, but it's absolutely essential. Like, the only way we could do this problem, factor it, would be to factor by grouping. We got 4 terms to start with this time. Okay? So first of all, could we factor out, I didn't even try in the last couple, we couldn't. Can I factor out a greatest common factor here? I can't, you're right. They don't all have variables, and this one only has a coefficient of 1, so there's nothing I can undistribute. So I'm stuck with those 4 terms, that's fine. But if I can factor something out, it always helps. Okay, so we'll split this thing down the middle. First group, what's my greatest common factor? I heard it.
Oh,
8x cubed, good. So 8's the biggest number I can undistribute. They both have variables, but this one's only got an x cubed. So that's the most I can undistribute. So I get 8x cubed for my greatest common factor. Now what's left behind? Well, I'll divide each term by 8x cubed to find out. What's 8x to the fourth divided by 8x cubed? X. Okay, 72x cubed divided by 8x cubed is 9. Good. Okay. So plus, I know I've got to have an x plus 9 out there. So you tell me, what times x is x? 1. So the greatest common factor in this case is just 1, right? For the second group. So what can I undistribute? X plus 9. Okay, what's left behind if I do that? This is a pretty cool little technique, isn't it?
Plus
Good. 8x cubed plus 1. Wow. Okay. And I was supposed to factor this completely. Okay, well, factoring by grouping, what did it accomplish? Now, the whole point of this, when we're playing this game of trying to factor polynomials, our goal is to break this into smaller and smaller pieces, a product of smaller pieces. By smaller pieces, though, what do I mean? Do I mean the number of terms? No. I mean the power of x. I want to break this into factors that have smaller and smaller pieces of x because they're easier to deal with, right? Ultimately, why do I factor things? Because I want to solve an equation. I want to apply the zero product property. Eventually, like this is kind of, these are just algebra 2 problems. Very seldom in math, in your life as a mathematician, if you're a mathematician, do you ever just factor stuff, just to factor it? You're factoring stuff in order to be able to solve an equation, or later on maybe cancel like factors and things like that. But you're factoring for a reason. For us, we're factoring to solve an equation, so we would be normally setting this thing equal to 0, right? If the original equation was set equal to 0, well, there's no way to handle that. It's a 4th degree polynomial. There is no quadratic formula equivalent for an equation like that. We've got to break this thing apart into small enough pieces that when we set the factors equal to 0, I'm getting miniature equations that I can solve, right? That's my whole strategy here. Okay, so can we go further? Well, if we were solving this equation, we would need to, because 8x cubed plus 1 is cubic. There is no cubic formula, right? So I got to go further. And you might be thinking, well, I could just set that equal to 0 and subtract 1 and divide by 8 in the cube root. And you're right. That would give me the real solution. But if I want to get all the solutions, that's not going to work. If I want all the complex solutions, I've got to keep on factoring this until I get down to quadratic factors or small or linear, right?
And we factor out the x cubed.
Okay, so now what about this one? This one's done, right? It's linear. It's got x to the 1 as the biggest power of x. But this one is cubic. What can I do to this one? There's no greatest common factor, right? But it is a 2-term polynomial, and what is my strategy for factoring a 2-term polynomial? Okay, the a cubed minus b cubed, a cubed plus b cubed, etc. So this is going to be a sum formula. Sum of squares or cubes?
So cubes.
Cubes, yeah, because I've got an x cubed plus something in it, right? So we want to use that pattern. So here we start, if we have an a cubed plus b cubed, and I want to split that into factors, what was my factoring pattern?
A plus B.
Plus b.
A squared minus AB plus B squared.
Good, okay? So that, if we can break this up into that pattern, if I can take this red factor and I can make it look like something squared, or something cubed, plus something cubed, then I can just follow that template and get it factored, right? So that's the big question though. Can I get this thing, can I write this whole thing as something cubed plus something cubed? Well, 1 is what cubed? 1 cubed. Okay, that one's easy. Well, what would I cube to get 8 times x cubed?
2x.
Okay, good. So now we know what our a is. This is our A, and that's our B, right? And we'll just follow this pattern. So this is gonna split up into A plus B. Now, what's A squared? This is where everyone's gonna make a mistake if you make a mistake.
Two x squared, but like parentheses.
Good, it'd be 2x quantity squared, so I gotta square the 2 and the x, and so I'm gonna get, when I do this A squared, I get 2x squared, which is 4 times x squared, right? Minus AB is gonna be 2x times 1 is 2x, and then plus B squared is just 1, right? And then over here, I've got my, can't forget that guy. There's a factor that was already done. So, and that's as far as I can go, isn't it? Right now, I've got this thing broken down where I've got a linear factor, and a quadratic factor. But remember, the trinomial that we get from the sum and difference of cubes patterns is irreducible. Don't even bother trying, and there'll be other factors. So that's as far as we can go factoring, okay? Make sense? All right. I want to get you going on this. Let's maybe just do one problem where we have to solve something. I won't do this one. Let's just do this one. We'll just do this one. That's good enough. Let's do this one instead. We'll just do one. Okay. So where should I push everything on this one?
Yeah.
To the right would make sense. I mean, we could go to the left and then, but let's keep the leading coefficient positive. So let's push everything to the right. So if I add 24x to the fifth to x to the fifth, I get what? 23x to the fifth plus x to the fifth would be 24x to the fifth. If I add 40x to the fourth to that side, I'm going to get a positive 40x to the fourth. Well, what if I add 4x cubed to negative 4x cubed?
Zero.
Just cancel.
Those cancel. Good. And then I'll add 81x squared to this side. There's no other x squared term. And if I add 127x to 8x, I get 135x. And then the other side is equal to 0, but let's put it on the right just because it looks better, right? So there's the equation we're starting with. Can I factor anything out to begin with? Because I want to if I can. What can I factor out? An x. Yeah, I could take an x out. No numbers, but I could take an x out of this whole thing. And if I do that, I'm left with x to the fourth, good, plus, very good, plus, plus. Okay, good, that helps a little bit. Well, we factored it a little bit. We've got it broken down into two factors that are slightly smaller, right? This one I gotta keep going with, right? I've got a 4-term polynomial, so how would I proceed to factor that further? What's my strategy for 4 terms? Grouping, good. So we're gonna factor by grouping. So then, now keep in mind, this is all inside the brackets. I like to put brackets up here when there's a big factor that's gonna get broken down further. Because then I'm gonna end up with brackets on the outside and maybe parentheses on the inside. It's easy to keep track, right? Okay, so in my first group, what's my greatest common factor?
8x.
8x to what, and what power of x? Third. Okay, good. That's pretty badass.
Oh no.
Yes.
Okay, so I get 8x cubed. Now what's left behind from that first group then?
24x. Oh wait, no. 3x.
3x, good. Plus 5, good. Okay. Plus, second group. First thing I do in the second group.
3x.
Okay. And then what times 3x is 81x?
12. 29. 28.
27. There you go. Okay, let's try it. It gives me 81x, and it gives me so it works. Okay, now watch carefully on this one, because this is an important step. So inside the brackets, I've got these two groups, these two terms. Is there a common factor I can factor out front? What is it gonna be? 3x plus 5. So where does it go? It goes out front with the x, right? So I've got my 3x plus 5 that got pulled out front. Now what's left inside my brackets then?
8x.
8x cubed plus 27. And at this point, do they really need to be brackets anymore? No, they can just be parentheses. They serve their purpose, right?
And now you can do it more.
And this whole thing is equal to 0, right? And so we got to go at least one more step, don't we? Because I've got an x cubed. Well, didn't we just do this one? No, it was a 1. So what would this is going to be a sum of cubes again, isn't it? Now what are our, there you go, 2x and 3, good. So we're going to get a 2x is our A, 3 is our B, right? And then that's going to split up into what? That's my A cubed plus B cubed. Good, 2x plus 3, there's A plus B, times 4x squared, very good, minus 6x, AB, plus,
No.
good, okay? And then out here, we can't forget these guys, we've got our 3x plus 5 and our x, right? And that's all equal to 0. Okay, so let's just take this and let's go to the next page, and we're almost done. Let's get all our zeros out of this guy. We've done all that hard work, now we get the payoff.
Just for one problem.
Yes.
How many problems
This is
are
what
on
I'm
this
not doing
assignment?
mathematician.
Not as many. These are shorter assignments. Okay, so now we just apply the zero product property, right? And that was our whole goal. We want to take that one big ugly fifth degree polynomial and break it up into a product of small factors. So when we set the factors equal to 0, we get simple equations to solve.
So we gotta solve this one?
Yeah. So if we set this factor equal to 0, we get x equals 0. There's our first solution. If we set this factor equal to 0, what are the two steps to isolate x? Subtract 5 to the other side and then divide by 3. So what's my solution? Good. Okay, how about this one? Good. Okay, here's the one that we gotta be a little careful with, right? Here's the one where we've got a quadratic, or quadratic factor. So we've got to, it's not gonna factor, we've got to use the quadratic formula. So we get x equals negative b, which is gonna be 6, plus or minus,
Square
this,
root.
there you go. There we go, right? Okay. So what do we get inside the radical? Let's focus on this one then. So we get x equals, let's split this up into separate fractions, right? Let's get rid of our common denominator. So we're gonna get 6 over 8, which we'll be able to reduce, plus or minus the square root of, so how would we do this? Here's how I would do this. When I multiply 4 by 9, I would say 4 times 9 is 36. Multiply by 4, you double and redouble. So 36 doubled is 72, doubled again is 144. So we're going to get inside the radical, we're going to get a 36 minus 144. What's that?
Something tells me where you get a 9.
Negative. There you go. Divided by 8. Okay, so now we just have to simplify that square root of 108. So let's take our 108 and let's figure out how we're going to, the negative is going to be an I, right? What about the 108? Let's break it up with a factor tree. What's it again? 9 and 12 works, there you go.
54 and 2. That
And 9 breaks up into, and 12 breaks up into 4 into 3, and 4 breaks up into?
2 and 2.
Okay, look what we get then. We get
Pair of 2s, pair of 3s.
couple of 3s, couple of 2s, and a single 3, right? So then x is equal to 6/8 just becomes 3/4, right? Plus or minus, what's the square root of 108 gonna be?
So we do the 6 over.
Okay, couple of 2s, couple of 3s gives me 6 outside,
And then 3 on the
3
inside, so I
inside.
have that side.
times the square root of 3, and then the whole thing is gonna be over 8,
Then times I.
and I've got an I out there, don't I? Because I've got a negative. Okay, so if I can just reduce those fractions, I got it. So x equals, harsh, everything. 3/4 plus or minus, that becomes a 3/4. So on the top, I'm gonna get a 3, radical 3 divided by 4. I. So there we go. We got, our zeros were 0, -5/3, -3/2, and then how many did I get here? How many zeros are there represented there? 2. 1 for the plus, 1 for the minus. It comes a complex conjugate pair. I's always come in pairs, and they come in pairs that are like A plus or minus B times I. So there's my A plus or minus B times I.
So that's an answer there. And so is.
So I'd have to put in,
0, -5/3.
yes, I have to put 5 answers and move.
Oh my gosh.
Okay? All right. That's pretty good for a day, don't you think?